What would you do if you knew how to save the planet from climate change? There are basically three types of climate films. Type 1 examines the problem, Type 2 looks at what we are doing about it, and Type 3 looks at what we would need to do to solve the entire problem at the lowest cost to society. No one has ever created a Type 3 film, possibly because the size of the problem and the size of the solution are difficult to comprehend. It is my goal to present the first Type 3 climate film, and do so in the most humane and responsible way possible. Many people are tired of hearing about climate change. For the most part, they have one simple question: how much does it cost to fix this? We will provide an estimate shortly. We will provide an estimate and explain how it was derived. But first, let's review the problem. Act 2, the problem. Section: the failure of decarbonization. Several decades ago, climate scientists stated we need to avoid a 1.5 degrees Celsius temperature increase relative to 150 years ago. This implies we are to crest at 1.5 degrees and then drop back down. Instead, we breached 1.5 degrees in 2023 and we are not cresting. Instead, we are warming rapidly. Also, carbon dioxide emissions would need to be close to zero at the point of cresting to cause global temperatures to decrease. Instead, actual emissions are at their highest level and are increasing. In other words, our society failed to transition to a green economy. It's even worse than that. We never were going to succeed. To understand why, we must look at this through the lens of economics. Section: the prisoner's dilemma problem. Harm comes from carbon dioxide emitted by 8 billion people. One person's own carbon dioxide is too small to be relevant. Therefore, each person does not benefit if they reduce their own emissions. Instead, each person wants the other 8 billion people to reduce. In economics, this is referred to as a prisoner's dilemma problem. And according to economic theory, our fundamental strategy of using social pressure to solve the climate problem was wrong from the start. Put differently, social pressure to decarbonize has little impact. One can see this in a graph that shows the percentage of global energy that does not emit carbon dioxide. This is all energy, not just electricity. And this is the entire world, not just one nation. As one can see, this has only increased from 14% to 18% over the past decade. At this pace, achieving full decarbonization would take approximately 200 years. Far too long to solve the climate problem. We can also look at the US, Europe and China. The US is on track to decarbonize over 250 years, Europe over 175 years, and China over 100 years. These graphs tell us social pressure has not and will not solve the climate problem. The only way to transition to a green economy over several decades is to enact laws that require decarbonization. The problem is, we would have had to enact these laws 30 years ago to get to zero emissions today, to cause global temperatures to crest at 1.5 and drop back down. Put differently, to solve the climate problem with carbon dioxide reduction, we would have had to enact decarbonization laws 30 years ago, which we did not do. Now that 1.5 has been breached, carbon dioxide is no longer our biggest problem. Instead, our biggest problem is runaway climate change. This is when changes to the planet accelerate, even with significant decarbonization. This is why scientists 30 years ago said, avoid 1.5 degrees Celsius. Acceleration is caused by self-reinforcing feedback loops that amplify existing forces. Unfortunately, we are currently observing acceleration in thawing permafrost, ocean current reduction, melting sea ice, and global warming itself. Acceleration is observed with actual measurements, so we know it is real. Due to acceleration, the next 30 years will see significantly more change than the previous 30 years. And a rapidly changing planet is a bad planet, since it means we have less time to adjust. Unfortunately, we are past the point where reducing carbon dioxide emissions will fix this. The acceleration problem is too great. Okay, if carbon dioxide reduction was Plan A, what is Plan B? Plan B is we change the atmosphere slightly to reflect more sunlight back into outer space. This would cool the planet slightly and stop acceleration. What happens if we don't do Plan B? What is Plan C? Plan C is runaway climate change. Here we take climate change on the chin and experience dramatic changes over the next 30 years. This would involve food shortages, mass migration, etc. And dealing with this is costly. Do we have other options? Yes, however, they are prohibitively expensive. So no, we don't have other options. In summary, Plan A will no longer fix this. And we are now looking at Plans B and C, neither of which are popular. Also, Plan B requires billions of dollars of R&D over the next 10 years, which we are currently not doing. Our society is facing two massive undertakings. One is carbon dioxide emissions reduction, and the other is reflecting sunlight. Reducing carbon dioxide emissions would be done by each nation, and reflecting sunlight would be done by multiple nations, since it involves the entire planet, not just sunlight above one nation. In other words, each nation needs a decarbonization plan, and all nations together need a global climate plan that involves reflecting sunlight. A plan would specify what needs to be done each year, the cost, and new laws that would drive it forward. Currently, plans do not exist. However, a website that creates plans could be developed. We'll talk more about this in a moment in our film. All of this might seem complicated and overwhelming. This begs the question, can we have someone take care of this? I mean, all of this. Currently, no one feels responsible for solving the entire problem. And that is part of the problem. In theory, a new laboratory could be set up to tackle the climate problem, the entire problem. Transitioning to a green economy is likely to cost $100 trillion globally over several decades. Therefore, spending something like $100 billion on a new lab to save trillions is reasonable. Let's run some numbers to get a better sense of this. If $100 billion was spent over 5 years, it would cost $20 billion each year. And if $500,000 was spent per technical person, this would employ 40,000 scientists and engineers. This goes way beyond what one university could handle. Therefore, money would need to flow toward many organizations. An example mission statement might be, save the planet from climate change at the lowest cost to society. In theory, faculty at universities could help set this up. Yet what might a new lab do to save us from climate change? We'll talk more about this shortly in our film. In summary, our current climate strategy is flawed in multiple ways. A plan to block runaway climate change does not exist. National decarbonization laws have been missing for 30 years. And 3, there is no mechanism that causes us to favor the lowest cost approach. All of this might sound terrible, and it is. However, it can be fixed using basic principles of science, engineering, and economics, and, in theory, this can be placed on the shoulders of one R&D laboratory that is tasked with solving the entire problem. We'll explain this further as we explore a plan to save the planet from climate change. Act 3, Reflecting Sunlight. Section Introduction. We're now going to talk about Plan B, which involves reflecting sunlight back into outer space. This is a new field and therefore requires research. The question for scientists is, how can we reflect approximately 1% of sunlight back into outer space at a reasonable cost without causing harm? We are already reflecting sunlight since it reflects off man-made air pollution. More specifically, it reflects off of sulfur. It's possible this is a key element in solving the climate problem. Let's explore this further. Section Sulfur 101. Sulfur is an element on the periodic table, and it is present in large amounts within coal and oil. Therefore, it is typically emitted into the atmosphere when these fuels are burned. Sulfur is harmful to people, plants, and oceans. Consequently, governments often require that some sulfur be filtered out before or after combustion. However, even with some filtration, approximately 70 million tons of sulfur dioxide gas, or SO2, are emitted globally into the atmosphere each year. After sulfur dioxide gas is emitted into the atmosphere, it typically combines with water and oxygen to form sulfuric acid. This nucleates, which means it converts to tiny physical particles. Water sticks to these particles and causes them to grow into physical water droplets. These droplets are so small and sparsely distributed that they are often imperceptible to the naked eye. Droplets containing sulfur typically reflect more sunlight than those without. Therefore, more sulfur causes more sunlight to reflect back into outer space instead of being absorbed by the planet. In effect, sulfur cools the planet. A notable example is the 1991 volcanic eruption of Mount Pinatubo, which released sulfur dioxide gas into the atmosphere, leading to a global temperature decrease of approximately 0.4 degrees Celsius. As mentioned previously, sulfur is present in coal and oil and is released during combustion. In theory, we can filter more of it out before combustion, transport the harvested sulfur to an airplane and emit it at a high altitude instead of at ground level. High-altitude sulfur stays aloft for 1 to 2 years, while ground-level sulfur typically stays aloft for only several days. Therefore, changing the emission site reduces the planet's temperature without increasing total sulfur emissions. The latter point is important since sulfur is harmful, as noted previously. Sulfur-based materials are not the only substances with reflective properties. For instance, calcium carbonate, commonly known as chalk, exhibits similar capabilities. Further research is needed to understand the benefits and drawbacks of each candidate material. To justify the expense, we would need to compare the cost of cooling the planet with the cost of not cooling the planet. One study suggests large-scale planet cooling would cost approximately $18 billion a year. For comparison, the total value of New York City property is $1,400 billion, and this is just one coastal city that would be lost to sea level rise. If the US paid half, planet cooling would amount to $27 per American per year. Increasing the reflectivity of the atmosphere is a new field, and there are many things we don't know. We don't know what to inject, when, where, and how. And we don't have an accurate assessment of costs and adverse side effects. To resolve unknowns, we need R&D. This includes developing better instrumentation for measuring atmospheric reflectivity, developing equipment that injects small amounts of material for field experiments, and developing equipment that injects large amounts of material for full-scale operations. And, as noted previously, we have a timing problem. To avoid runaway climate change, our society would need to spend significantly more money on atmospheric reflectivity, R&D. In summary, Plan B does exist. However, it is not popular and is therefore mostly being ignored. This is in part due to our denial that Plan A failed due to undersized decarbonisation efforts. In conclusion, it is reasonable to support Plan B with extensive research and development. We will now talk about Plan C, which is runaway climate change. In review, Plan A, which is decarbonisation, failed. We know this because we breached the 1.5-degree threshold in 2023 with a rapid warming rate and high carbon dioxide emissions. We still have Plan B, which is reflecting sunlight. However, it is not popular and is therefore mostly being ignored. Subsequently, we are headed toward Plan C, which involves significant changes to our planet over the next few decades. This is difficult to discuss for several reasons. 1, it is upsetting. 2, it is difficult to comprehend significant changes to our planet. And 3, many people still believe Plan A is viable, in part due to decarbonisation news reports that appear almost daily. In spite of these difficulties, we will press forward. We will begin with a review of tipping points. Tipping points are additional sources of global warming that add to global warming already being done by carbon dioxide. An example is North Pole sea ice. It is 1 to 2 meters thick, and when it melts, sunlight is absorbed by seawater instead of being reflected by sea ice, and this causes the temperature of the planet to increase. There are approximately 5 million square kilometers of sea ice around the North Pole. This is about half the size of the United States. If this were to melt, the average global temperature would increase by 0.6 degrees Celsius, and this would add to the 1.5 degrees of global warming already done by 150 years of carbon dioxide and methane emissions. In other words, global warming would accelerate due to this tipping point and other factors. Thawing permafrost is another tipping point. It releases methane, a greenhouse gas, which also causes the planet's temperature to increase. Unfortunately, more heat causes more permafrost to melt in a self-reinforcing cycle, and this also causes global warming to accelerate. There are approximately a dozen tipping points that are capable of increasing the average global temperature. They do this after being activated, and they are activated by heat. In other words, tipping points activate each other and are therefore like dominoes. One of the first dominoes to tip will probably be North Pole sea ice. After this melts, the Arctic region will become warmer, and this will cause snow and ice on Greenland to melt. Unfortunately, this will dump fresh water into the Atlantic Ocean, which will reduce ocean currents. These currents move heat from the equator to Europe, and a loss of this flux will make the former warmer and the latter colder. Ultimately, this will lead to less food production, mass migration, etc. As noted previously, a quickly changing planet is a bad planet, and Plan C is a quickly changing planet. All of this might sound terrible, and it is. Also, a reasonable path forward does exist. We will explore this path in our next video. Act 5, the climate change solution. Section Introduction. We will now look at how to solve the entire climate problem at the lowest cost to society. This is not being done, yet could be done. We will begin by exploring the concept of a climate plan. Section Climate Plan. Lawmakers are not inclined to support major changes to their economy without a detailed plan. This does not exist, yet could be developed. A detailed plan would be a list of decarbonisation initiatives to be implemented each year over the next few decades. For each initiative, the following would be estimated cost in dollars, tons of carbon dioxide reduced, and the cost per ton of carbon dioxide reduced. Government-employed energy economists are capable of estimating these values and are somewhat trusted by lawmakers. Therefore, they would probably be needed to help formulate a climate plan. However, they will only act if commissioned by lawmakers and driven by a guiding principle. To achieve majority support, the guiding principle would need to meet the satisfaction of both liberals and conservatives who are concerned about climate. Survey data indicates 67% of Americans are concerned about climate change, suggesting bipartisan support is achievable. Based on statements made by lawmakers on both sides, the following guiding principle would probably receive support. Decarbonize at the lowest cost to society over 30 to 40 years at a constant rate, in lowest cost order, without taxes, without subsidies, and with additional costs passed on to consumers. Taxes and subsidies do not have broad political support at large scales due to several issues. These include deficit spending, economic efficiency, sensitivity to fuel price, control over the decarbonization rate, and fraudulent offsets. Requirements, on the other hand, do not have these problems. Many lawmakers ask, why spend $200 to reduce emissions by 1 ton of carbon dioxide when we can do it for $20? This implies they want to decarbonize in lowest cost order. For example, tackle $20 per ton initiatives first, followed by $25 per ton. A climate plan would be influenced by policy options. In theory, government economists could be tasked with building a website that generates a climate plan after the website user specifies policy options. Many conservatives are fond of green energy. However, they typically require a lowest cost approach, while liberals are often less demanding. Texas, a conservative state, produces more wind power than any other US state, suggesting conservatives are comfortable with green energy at large scales. Many climate initiatives are not effective or not cost efficient. This is because people sell climate to make money, and the impact of their efforts are rarely quantified. This is why government energy economists are needed to evaluate initiatives and help craft a climate plan. For the most part, government needs to require transitioning to a green economy. For example, power companies could be required to decarbonize the grid by 2035. Builders of solar farms and wind farms would then compete with each other and drive down costs. How much would this cost a US homeowner? Let's calculate the additional cost of a green grid for the typical US homeowner. On most home electric bills, electricity consumption is specified in units of kilowatt hours or kWh. For example, operating a vacuum cleaner for an hour uses approximately 1 kWh of electricity. The typical US home consumes 10,000 kWh each year at 14 cents per kWh for a total of $1,400 per year. This is retail cost, and it covers electricity generation and distribution. Generation refers to making electricity at the power plant, while distribution refers to the network of power wires between generation plants and consumers. Typically, 7 cents per kWh goes to generation and 7 cents to distribution. Green electricity, which is produced without emitting carbon dioxide, typically costs 1 to 2 cents more per kWh than non-green electricity. Currently, 40% of US electricity is green. Therefore, 60% needs to be decarbonized. If this were done over 12 years, then 5% would be decarbonized each year. According to the math, 5% of 10,000 kWh at an additional 2 cents per kWh is $10 per year. Therefore, the additional cost per household would be $10 in the first year, $20 in the second year, $30 in the third year, and so on. Nations meet annually at COP conferences to supposedly agree on how to tackle climate change. However, in many cases, little is achieved. This is partly due to conference attendees' lack of authority to create laws. So what is an intermediate step short of real decarbonization that nations might agree to? One possibility is for nations to commit to spending 0.01% of their annual GDP on additional climate R&D. In the United States, this would equate annually to about $2.7 billion or $8 per American. Nations would need to agree on what constitutes additional climate R&D. These would be things that are not currently being pursued and have the potential for significant impact. In theory, a national leader could ask government scientists to calculate how much sunlight needs to be reflected to block cascading tipping points and identify how to do this at lowest cost without harm. Currently, a global climate plan does not exist. However, with a little prodding from leadership, it could be developed. Resolving climate change involves three basic questions. How can we solve the entire climate problem at the lowest cost to society? What actions would this entail? How much would this cost? An estimate is provided below. All numbers are in units of dollars cost per American per year. Europeans would see similar numbers. These costs would show up as an increase in the cost of goods and services, in addition to government spending. This table divides costs into three areas, reflecting sunlight or planet cooling, the additional cost of green products known as the green premium, and additional R&D. It is assumed decarbonization occurs at a constant rate over 30 years, with initial decarbonization costs starting at $20 per ton of carbon dioxide reduced and increasing to $80 per ton. To calculate the additional cost of green products per American during year one can divide total annual carbon dioxide emissions by 30 years, multiply by $20 per ton, and divide by the US population. The math works out to $10. The left side of the table examines costs for years 1, 2, and 3, while the right side looks at years 10, 20, and 30. One might think of these as the early years and the later years. The early years are relatively easy, since decarbonization costs are proportional to the amount of carbon dioxide reduced, and initially this would be small. As evidence of climate harm continues to grow, the public's willingness to bear decarbonization costs is likely to increase. To address climate change, we need costs to stay below tolerance of costs as we go through time. For example, we need the public to accept approximately $35 per American per year during the early years when people are moderately concerned about climate, and accept hundreds of dollars per American per year during the later years when people are more nervous. A reasonable strategy during the early years is to focus on lowest cost decarbonization and more R&D. During the first 5 years, many nations could reduce carbon dioxide emissions by approximately 1/30 each year by building solar farms and wind farms. This would cost roughly $20 per ton of carbon dioxide reduced. During this initial period, billions of dollars could be spent on R&D for commercial fusion and improved fission. Either of these might be needed for times when the sun does not shine and the wind does not blow. Currently, people do not want to touch the atmosphere. However, this will probably change, as climate observations provide evidence that touching is easier than not touching. Therefore, a reasonable strategy is to conduct reflectivity R&D while public opinion evolves, followed by small-scale pilot projects and ultimately large-scale implementations. At some point, climate observations will probably cause our society to panic. When and if this occurs, we need to be prepared with a lowest cost approach. Otherwise, we are at risk of running out of money before making significant progress. Fortunately, preparing to panic is relatively inexpensive since it only involves plan development, more R&D, and small-scale operations. We'll talk more about this as we explore a plan to save the planet from climate change.